Alright, so this will be our last video on matrix inverses. In this video we're going to discuss how to actually compute the inverse of a matrix in terms of elementary matrices, and also how to then write the original matrix as a product of elementary matrices. Okay, so we discussed in the last video that if I want to invert an elementary matrix, I just have to do the opposite row operation, right? So if so let's say that I start with the identity matrix, and let's do sort of let's do 3 by 3 identity matrix, and let's say I swap row 1 and row 3. Okay, so that gets me to 0 0 1 0 1 0 0 oops 1 0 0. Okay, so let's say that's my E. Okay, well, if I then swap those guys again, right, I would get back to the identity matrix. But I know also that the other way of applying this row operation to my matrix E, right? If I want to apply the row operation which switches row 1 and row 3, if I want to apply that to E, well, that's the same thing as, we know that applying a row operation is the same thing as multiplying on the left. So E times E is the identity. That tells me that E is its own inverse. And in fact, every type 1 elementary matrix is its own inverse. Okay. Similarly, if I took if I did, let's say I do let's say I multiply row 1 by 1 over 4. Okay. And that gets me to 1 over 4, 0, 0, 0, 1, 0, 0, 1, right? If I wanted to get back, so this is my E in this case, if I wanted to get back to the identity, how would I do it? I would multiply row 1 by 4. 4 row 1 to row 1, and I'm back to the identity, right? But I also know that that this row operation here, this is encoded by an elementary matrix, which for reasons as above must be the inverse of the one I started with. And so this is 4 0 0 0 1 0 0 1, right? So that's got to work, because if I do E inverse times E, right, applying this elementary matrix to this guy performs. So if I take this elementary matrix and I multiply on the left by this matrix, right, so E inverse times E, well, multiplying E on the left by E inverse performs this row operation, which takes me to the identity. So I get back to the identity, right? Similarly, if I did, let's say I do row 2 minus 4 row 1 becomes my new row 2. So 1 0 0 minus 4 1 0 0 0 1. Okay, if that's my E, and I wanted to get back to the identity, how would I get back to the identity? Well, I'd have to get rid of that minus 4. How would I get rid of the minus 4? I'd have to take 4 times row 1 and add it. So I have to do row 2 plus, right? Instead of adding, instead of subtracting, we add. Or if I had originally added, I would subtract. And that takes me back to the identity. And so again, we would argue that the inverse must be 1 0 0 4 0, so 4 1 0 0 0 1, right? So to invert an elementary matrix, you just do the opposite row operation. Okay, so now let's say I have a matrix. I want to write it as a product of elementary matrices. Here's what we do. We start with our matrix, 3 minus 9 minus 1, 6. Let's do some row operations. First thing we need is a leading 1. Let's divide row 1 by 3. So I'm going to do 1/3 row 1. It's going to be my new row 1. And that gets me to 1 minus 3 minus 1 6. Okay, so what is my elementary matrix? Let's call that E1. E1 is the elementary matrix I get if I take this row operation and I do it to the identity. That gives me 1/3, 0, 0, 1. What's the inverse? I do the opposite thing to the identity. The opposite of dividing by 3 is multiplying by 3. So 3, 0, 0, 1. Okay. Next up, what am I going to do? I'm going to use my leading one to get rid of the minus 1 below it. So I'm going to do row 2 plus row 1. It's my new row 2. 1 minus 3. 0, 3. Okay. So E2 is going to be 1, 0, 1, 1. And the inverse, instead of adding, I subtract. 1, 0, minus 1, 1. Okay. What's next? Next up, I've got to do 1/3 row 2. Becomes row 2. 1 minus 3. 0, 1. So E3 is 1, 0, 0, 1/3. The inverse, instead of dividing by 3, I multiply by 3. Okay, one more. What's the last step? The last step is get rid of that minus 3. So to do that, I've got to do row 1 plus 3 row 2. That's going to be my new row 1. 1, 0, 0, 1, which is my identity. And so I get an E4, which is going to be 1, 3, 0, 1. And the inverse is going to be, instead of adding that 3, I would subtract the 3. So 1 minus 3, 0, 1. Okay. So now I've done all my work. I've got my elementary matrices. I've got their inverses. Let me kind of separate those out. Let me also shorten this line slightly so we got some room at the bottom. Okay, so where do we go from here? Well, remember that the inverse, we saw this in the previous video, the inverse is you take your elementary matrices. Actually, let me put this at the top. Okay, so for reference, our theorem said that the inverse is given by multiplying our elementary matrices, but we multiply in this descending order, 4, 3, 2, 1, not 1, 2, 3, 4. And then A is given by inverting this product, and when we invert the product, we reverse the order. So we get the inverses in ascending order, right? So to calculate A inverse, I take my elementary matrices and multiply in descending order. To invert things, I multiply the inverses in ascending order. So the inverse, well, I don't need to write it. The question didn't ask me to write out A inverse, so if I wanted to, I could. If I want to write A, it's going to be 3, 0, 0, 1. There's E1 inverse times E2 inverse, 1, 0, minus 1, 1, times E3 inverse, 1, 0, 0, 3, and E4 inverse, 1, minus 3, 0, 1. And I'll leave it to you guys to multiply those four matrices together and confirm that you do, in fact, get back the original matrix A. Okay. One more example, 3 by 3. We'll go through the exact same procedure. Let me kind of try to do this one a little bit more quickly. Okay, 1, 0, 2, minus 1. I'm going to work my way across with the row operations. Okay. So we're going to do row 2 plus row 1 into row 2. That's going to be, and let me just kind of number them. That's going to be the first thing I do. The next one I'm going to do is row 3 minus 2 row 1 into row 3. By the way, it doesn't matter, we know that it doesn't matter whether you do 1 and then 2 or the 2 and then 1. This is a case where the order in which we do these two row operations doesn't matter, right? Because they affect different rows. So this is one case where the corresponding elementary matrices, actually it doesn't matter the order in which I multiply those ones together. Normally order of multiplication matters, but actually you can see that in this case it doesn't. Okay, so we get 0, 0, 1. Okay, you can see I set this one up to go rather quickly, and because I only have so much space on these slides, so I need 2 more row operations and we're going to get there. Row operation 3 is going to be row 1 minus 2 row 3 into row 1, and then 4 is going to be row 2 minus 2 row 3 into row 2, and I'm done. Right? And again, the operations 3 and 4 are interchangeable, but 2 and 3, for example, or 2 and 4, those I can't swap that order, right? The first two are interchangeable, the second two are interchangeable, but as a set of 4, the order really does matter, okay? So my matrices are E1 is going to be okay, 1 0 0 1 1 0 0 1. E2 is going to be, so row 3 minus 2 row 1 1 0 0 0 1 0 minus 2 0 1. E3, row 1 minus 2 row 3 1 0 minus 2 0 1 0 0 0 1. E4, my E2 was a bit too fat. Let's squeeze it in. 0 0 1 minus 2, made it. Okay, there we go. Sorry about the compression. And so if I wanted to write, again, if I wanted to write the inverse, this one didn't ask me for the inverse, but if I wanted the inverse, it would be E4 times E3 times E2 times E1. The original matrix is going to be E1 inverse, E2 inverse, E3 inverse, E4 inverse. So the inverse of E1, instead of that plus 1, I need a minus 1. The inverse of E2, instead of that minus 2, I need a plus 2. The inverse of E3, that minus 2 becomes a plus 2. Inverse of E4, again that minus 2 becomes a plus 2. And we're done. Okay, so that's it for matrix inverses. In the next set of videos, which I'll hopefully get posted tomorrow, we'll move on to some other operations on matrices, namely the transpose, the trace, and the determinant.